Picture this. You are standing alone in the middle of a vast, open field. Darkness surrounds you. Above your head, massive, pitch-black clouds are churning like a living beast. Then, in a fraction of a second, a single spear of light, hotter than the surface of the sun, rips through the sky. This bolt carries millions of volts of electricity. Its roar is so loud it can be heard from over 10 miles away. This isn't a scene from a sci-fi blockbuster. This is one of the most common, yet most profoundly mysterious, phenomena on our planet. This is lightning. Welcome back to Night Tales, Docs. Today, we are venturing into the electrifying heart of this celestial monster to uncover some truly mesmerizing facts. Did you know that roughly 100 lightning bolts strike the Earth every single second? Yet, hidden within this everyday spectacle are secrets so bizarre, so awe-inspiring, that they will completely change how you look at a stormy sky. So, sit back, relax, and let's embark on this electric journey. The genesis of lightning, when the sky rebels. We often describe lightning as the wrath of the gods, or the sky rebelling. But science tells us a different story. It is actually nature's way of restoring balance, a massive electrostatic discharge that neutralizes the tension between the Earth and the clouds. In this chapter, we'll uncover exactly how this incredible event is born. Our journey begins about an hour earlier, with the formation of a cumulonimbus cloud, the thundercloud. These clouds are colossal, towering up to 15 to 20 kilometers into the atmosphere. The inside of this cloud is a chaotic factory. Powerful updrafts and downdrafts of air collide violently. As they do, the water droplets and ice crystals inside the cloud rub against each other relentlessly. Here's a fascinating fact. The top of the cloud is well below freezing, while the bottom is relatively warmer. It is this extreme temperature difference that holds the key to the entire electrical dance. As tiny ice particles, known as gropal, are tossed up and down in the turbulent air, something strange happens. Lighter ice particles are carried upward, while the heavier gropal sinks downwards. During these collisions, electrons are stripped off and transferred. The gropal becomes negatively charged, while the lighter particles become positively charged. What is the result? The top of the cloud becomes a massive reservoir of positive charge, while the bottom becomes heavily negative. This charge difference grows so immense that the cloud essentially turns into a giant battery. When the electrical potential becomes too great for the air to resist, lightning is born. We usually only see the blinding flash of the main strike, but an invisible process happens first. The negative charge at the bottom of the cloud is strongly attracted to the positive charge building up on the ground below. To bridge this gap, the cloud sends down an invisible, ionized path of air called the stepped leader. This leader doesn't travel in a straight line. It moves down in a series of rapid, jerky steps, about 50 meters at a time, at a speed of roughly 200 kilometers per second. We can't see it because it is incredibly faint. As this leader approaches the ground, the intense electric field causes a surge of positive charge from the ground to reach upward in what is called an upward streamer. When the downward leader and the upward streamer meet, the circuit is complete and the main strike occurs. The moment these two paths connect, a massive electrical current surges upward from the ground to the cloud at incredible speed. This is the return stroke, the blinding flash we actually see. The temperature of this stroke reaches a staggering 30,000 Kelvin. To put that in perspective, that is roughly 5 times hotter than the surface of the sun, which is about 5,778 Kelvin. As this return stroke travels upward, it heats the surrounding air so explosively fast that the air expands violently, creating a shock wave. This shockwave is what we hear as the rolling, rumbling sound of thunder, the weird and wonderful forms of lightning. Lightning isn't just a single bolt shooting from the sky to the ground. It has an entire family of bizarre, mysterious, and mind-bending forms that scientists are still trying to fully understand. In this chapter, we'll look at the strangest members of the lightning family. Did you know lightning doesn't just strike downward? Above the clouds, stretching into the stratosphere and even the ionosphere, are spectacular displays called transient luminous events, or TLEs. First, there are sprites. These are massive, reddish-orange flashes of light that can extend up to 90 kilometers above the cloud tops. They are often shaped like giant jellyfish or carrots. Sprites are incredibly brief, lasting only a few milliseconds, and their existence was entirely unknown to science until 1989. Then, there are blue jets. These are conical blue flashes that shoot directly upward from the top of thunderclouds, reaching up to 50 kilometers. They are even more elusive than sprites, and the exact mechanism driving them remains a topic of active research. Finally, there are Elves. This is an acronym for emission of light and very low-frequency perturbations due to electromagnetic pulse sources. They appear as rapidly expanding, donut-shaped rings of light that spread out in the ionosphere. They are caused by the electromagnetic pulse from a powerful lightning strike. For centuries, people have reported witnessing a truly bizarre phenomenon: glowing, floating orbs of fire that drift through the air, hover near the ground, and then vanish with a bang or a whimper. This is called ball lightning. While many scientists dismiss these reports as optical illusions, recent studies suggest they are real. It is a glowing, spherical object that usually appears during or after a thunderstorm. They can range in size from a small tennis ball to a large beach ball and come in colors like yellow, red, blue, or white. Scientists hypothesize they are formed when lightning strikes the ground, vaporizing silicon or other minerals in the soil, which then slowly oxidize in the air, creating a glowing plasma ball. The lightning we typically see originates from the negatively charged bottom of the cloud and strikes the positively charged ground. However, there is another, far more dangerous type: positive lightning. This bolt originates from the positively charged top of the cloud and strikes the ground. These strikes are roughly 10 times more powerful than a normal lightning bolt and last much longer. Because they originate from the top of the cloud, they travel much further horizontally before hitting the ground, sometimes striking miles away from the storm itself, what we call a bolt from the blue. Due to its immense power, positive lightning is far more destructive and is notorious for starting massive wildfires. The mathematics of a monster, astonishing statistics. To truly comprehend the power of lightning, we have to look at the numbers. They are so extreme that they often seem like science fiction. In this chapter, we break down the mind-boggling stats of nature's electric show. First, speed. Lightning travels at an average speed of 220,000 kilometers per hour. To put that in perspective, it could travel from New York to Los Angeles in roughly the time it takes you to blink. Second, temperature. As mentioned, the return stroke hits 30,000 Kelvin. At this temperature, the silica in sand fuses into glass. That is exactly why, when lightning strikes a sandy beach or desert, it leaves behind hollow, branching glass tubes called fulgurites, often referred to as petrified lightning. Third, energy. A single stroke of lightning can carry up to 1 billion volts of electricity and up to 30,000 amperes of current. That is enough instantaneous power to light 100 million LED bulbs for a split second. Fourth, frequency. Globally, an average of 100 lightning strikes occur every single second. That means in the time it takes you to watch this documentary, thousands of lightning bolts have already struck somewhere on the planet. Fifth, the longest bolt. In 2018, a single megaflash stretched for an incredible 709 kilometers across the sky over Brazil. To visualize that, it's the distance from London to Berlin. And 6, the longest duration. The longest-lasting lightning flash on record occurred over Argentina in 2019, lasting a mind-blowing 16.73 seconds. That is an eternity for a single bolt of lightning. Lightning and our lives, the giver and the taker. We often view lightning solely as a destructive force. While it is indeed terrifying, lightning also plays a surprisingly beneficial and crucial role in supporting life on Earth. In this chapter, we weigh the good, the bad, and the bizarre. Did you know that lightning is a natural fertilizer machine? Our atmosphere is composed of about 78% nitrogen. However, plants cannot absorb this gaseous nitrogen directly. They need it in the form of nitrates. The immense heat and energy of a lightning bolt force the nitrogen and oxygen in the air to react chemically, producing nitrates. These nitrates are washed down to the earth by rain, effectively fertilizing the soil. Scientists estimate that lightning contributes to roughly 10% of all natural nitrogen fixation on the planet. Without this electrical boost, the greenery of our planet would look vastly different. Furthermore, the high-energy electrons released during a lightning strike can break apart oxygen molecules in the atmosphere, allowing them to recombine into ozone. While the amount is minuscule compared to industrial pollution, it does play a minor role in maintaining the chemical balance of the ozone layer in the stratosphere. Naturally, we cannot ignore the terror lightning brings. It is estimated that lightning kills approximately 24,000 people globally every year, with tens of thousands more suffering severe, lifelong injuries. A direct strike can cause immediate cardiac arrest and severe neurological damage. Even an indirect strike, with current traveling through the ground, can cause burns, fractures, and memory loss. Survivors often suffer from fulgurite trauma, where the electrical current causes intricate, tree-like red patterns to burn into their skin. Lightning is also responsible for billions of dollars in damage annually, from destroying electronics in homes to sparking catastrophic wildfires that raze thousands of acres of forest. Despite the danger, there are unbelievable tales of survival. Take Roy Sullivan, a park ranger in the US. He holds the record for being struck by lightning 7 times and surviving every single strike. Furthermore, survivors often bear temporary markings called Lichtenberg figures, or lightning flowers. These are fern-like patterns on the skin caused by the rupture of superficial blood vessels due to the electrical discharge. They are not burns, but beautiful, branching scars that usually fade away within a few days. The unsolved mysteries, what we still don't know. Despite centuries of study, lightning stubbornly clings to many of its secrets. In this chapter, we explore the frontiers of lightning science, the questions that leave even the brightest scientists scratching their heads. In recent years, scientists have made a shocking discovery. Lightning emits intense bursts of X-rays and even gamma rays. But how does a simple electrical discharge generate such high-energy, astrophysical-level radiation? The leading theory is that the extreme electric fields in a lightning strike accelerate electrons to near the speed of light. When these electrons hit air molecules, they emit X-rays through a process called Bremsstrahlung, or breaking radiation. This discovery has completely turned our understanding of lightning physics upside down. Perhaps the strangest mystery is dark lightning. Unlike ordinary lightning, this phenomenon produces almost no visible flash. Instead, it generates a massive burst of gamma-ray radiation, a terrestrial gamma-ray flash. It is so powerful that it could pose a radiation risk to passengers in airplanes flying directly above a thunderstorm. We are only just beginning to understand how these invisible, silent pulses work. As global temperatures rise, scientists are predicting a significant increase in the frequency of lightning strikes. Warmer air holds more water vapor, and more moisture leads to stronger updrafts and more energetic thunderstorms. Some models suggest that for every 1 degree Celsius of warming, we could see a 10% increase in lightning activity. This means the future might not just be hotter, but much more electrically violent. How to stay safe, your lightning survival guide. In our final chapter, we move from the theoretical to the practical. While lightning is awe-inspiring, respect for its power is essential. Here are some life-saving tips to keep you safe in a storm. First, follow the 30-30 rule. If the time between seeing the lightning flash and hearing the thunder is 30 seconds or less, seek shelter immediately. Wait at least 30 minutes after the last clap of thunder before leaving your safe spot. Second, if you are caught in a field, your car is a surprisingly safe place. The metal frame acts as a Faraday cage, directing the electrical current around the outside of the vehicle and safely into the ground. Just make sure you don't touch any metal parts inside. Third, never take shelter under a tree. This is one of the most common mistakes. Tall, isolated trees are lightning rods. Taking shelter underneath one makes you vulnerable to a side flash, where the lightning jumps from the tree to you. Fourth, avoid water. Water conducts electricity. During a storm, avoid taking showers, washing dishes, or touching plumbing fixtures. Lightning can travel through the metal pipes in your house. Fifth, if you are completely exposed and have no shelter, your best bet is to minimize your contact with the ground. Crouch down with your feet together, tuck your head in, and cover your ears. Never lie flat on the ground, as the electrical current can flow horizontally over the Earth's surface and through your body. Lightning is a humbling reminder of the immense forces that exist just beyond our fingertips. It whispers to us, or rather, it roars at us, that we are not the masters of this planet. The universe is far more powerful, far more bizarre, and infinitely more beautiful than we can often comprehend. Our best response is awe, respect, and an insatiable curiosity to keep learning. Lightning beyond Earth. The electric planets. We tend to think of lightning as a uniquely terrestrial phenomenon, a product of our particular atmosphere and water cycle. But we would be profoundly wrong. Earth is not the only place in the solar system where the skies crackle with electricity. In fact, some of our planetary neighbors host storms so vast and so powerful that they make our most violent thunderstorms look like a passing drizzle. Let us start with Jupiter, the largest planet in our solar system. Jupiter is a gas giant, a world of swirling hydrogen and helium, banded with colorful clouds. For centuries, astronomers have observed the Great Red Spot, a massive storm larger than the entire Earth. But hidden within Jupiter's turbulent atmosphere are lightning bolts that are truly astronomical in scale. Data from the Juno spacecraft, which orbits Jupiter, has revealed lightning that is up to 100 times more powerful than the lightning we experience on Earth. The radio signals emitted by these Jovian strikes, called whistlers, are so loud that they can be detected across millions of kilometers. The reason for this immense power is the deep, dense atmosphere of Jupiter, where the pressure is so high that water exists in exotic metallic states, creating colossal charge separations. A single bolt on Jupiter could light up an entire country. But Jupiter is not alone. Saturn, famous for its stunning rings, also hosts massive electrical storms. These storms are so massive that they can wrap around the entire planet, creating a giant, glowing hexagon at its north pole. The lightning on Saturn, while less frequent than on Jupiter, is still thousands of times more energetic than Earth's. Scientists believe that the storms on Saturn are seasonal, erupting with such ferocity during certain periods that they can be seen from Earth-based telescopes. What about Venus? Our sister planet is a hellish world of sulfuric acid clouds and surface temperatures hot enough to melt lead. For years, the presence of lightning on Venus was hotly debated, but recent data from the Venus Express probe has provided compelling evidence of widespread, persistent lightning in the Venusian atmosphere. However, unlike Earth, where lightning occurs in the water-rich lower atmosphere, the lightning on Venus is thought to occur high up in the sulfuric acid clouds, sparked by volcanic activity or the friction of ash and dust particles. It is a stark reminder that electricity is a universal language, spoken across the cosmos, regardless of the chemical composition of the planet. Dirty thunderstorms, when Earth erupts in flames. If planetary lightning is the most extreme in scale, then volcanic lightning is perhaps the most dramatic and awe-inspiring sight on our own planet. Imagine a massive volcano spewing a plume of ash and gas tens of kilometers into the atmosphere. This ash plume is not just a cloud of rock dust, it is a raging, violent factory of static electricity. This phenomenon is known as a dirty thunderstorm, and it represents a terrifying convergence of nature's most destructive forces, fire and electricity. When a volcano erupts, it ejects a massive column of ash particles, rock fragments, and ice crystals. As these particles are blasted into the air with immense force, they collide, rub together, and fracture, much like the ice crystals in a thundercloud. This friction strips electrons from the particles, creating massive charge separation within the ash plume. The lighter, positively charged particles rise higher, while the heavier, negatively charged ash falls back towards the crater. The resulting electrical potential is staggering. As the charge difference builds, the ash plume crackles with thousands of lightning bolts, often happening simultaneously. The most famous example of this was the 2010 eruption of Eyjafjallajökull in Iceland, which grounded air travel across Europe, or the incredible eruption of Chile's Calbuco volcano in 2015, where lightning danced through the towering ash cloud as if the mountain itself had become a live wire. There is something deeply primeval and terrifying about volcanic lightning. It is as if the earth itself is screaming, and the lightning is the visual manifestation of that scream. The bolts do not just strike the ground, they strike sideways, upward, and directly through the heart of the ash column, creating a mesmerizing, apocalyptic light show. Scientists study these events to understand the charge dynamics of eruption plumes, hoping that one day, a sudden increase in volcanic lightning could serve as an early warning system for an impending, catastrophic eruption. Chapter 3: The Invisible Sky Dancers, Trolls, Pixies, and Gigantic Jets. In our previous session, we briefly touched upon the upper atmosphere phenomena like Sprites and Elves. But the upper atmosphere holds far more secrets than just those two. There is a hidden world of fleeting, colourful, and massive electrical discharges that occur far above the clouds, phenomena that were completely unknown until the late 20th century. Let us explore the world of gigantic jets. While Sprites are known to stretch up to 90 kilometers, gigantic jets are the true giants of the upper atmosphere. They are triggered by a massive charge imbalance within the thundercloud, but instead of striking down, they shoot upward with incredible speed, directly connecting the top of the thundercloud to the ionosphere, which is over 100 kilometers above the Earth's surface. They are shaped like a colossal tree trunk, with branching tendrils spreading out at the top. They are incredibly rare and last less than a second, making them one of the most difficult lightning phenomena to photograph. Then we have the trolls, Yes, scientists, in their wonderful sense of whimsy, named a type of transient luminous event a troll. Trolls are essentially red sprites that have been significantly distorted by gravity waves in the upper atmosphere. They appear as glowing, jellyfish-like blobs with distinct, elongated tendrils, drifting horizontally rather than vertically. They are the special effects of the magnetosphere, triggered by the brutal electric shock of a cloud-to-ground strike. And let us not forget the pixies. Pixies are small, extremely brief, isolated blue patches of light that appear in the mesosphere, usually at the lower altitude end of the Sprite spectrum. They are thought to be the optical signature of small, powerful electrical discharges in the upper atmosphere, far weaker than a full Sprite, but equally mysterious. What is truly mesmerizing about these upper atmosphere events is that they change the way we think about the Earth's atmospheric system. We used to think the atmosphere was layered, with the troposphere doing its thing, and the ionosphere being a distant, passive layer. Now we know that a thunderstorm on the ground sends electromagnetic pulses and massive electrical charges all the way to the edge of space, painting the sky with colors we cannot even see with our naked eyes. The acoustics of rage, why thunder rolls. We have talked extensively about the light of lightning, but what about the sound? We all know thunder as the deep, rumbling roar that follows a flash. But have you ever stopped to wonder why thunder rolls? Why does it not just sound like a simple, sharp crack? The answer lies in the physical path of the lightning itself. Imagine you are looking at a lightning bolt. It is not a single, straight line. It is a jagged, zigzagging tree of electricity, sprawling across the sky for miles. The sound of thunder is generated along the entire length of that jagged channel. The return stroke heats the air along the entire path almost simultaneously, creating a shock wave along that complex, three-dimensional shape. Now, consider the speed of sound versus the speed of light. Light travels to your eyes almost instantly. Sound travels much slower. The sound originating from the part of the bolt closest to you reaches your ears first, while the sound from the upper branches of the bolt, which are miles away, takes a fraction of a second longer to reach you. This continuous, staggered arrival of sound waves from different distances along the winding lightning channel is what creates the prolonged, rolling rumble we associate with thunder. If the lightning is a relatively straight, vertical strike directly above you, the sound arrives all at once, creating a sharp, deafening crack that shakes your bones. But if the lightning is a sprawling, horizontal network of branches across the sky, the sound is dragged out into a long, low growl, like a giant rolling a boulder across the sky. Furthermore, the atmosphere itself plays a role. Sound waves bend and refract due to temperature and wind conditions. In a temperature inversion, where the air is warmer above than below, sound can be bent back down towards the ground, allowing thunder to be heard much further away than usual. Nature, it seems, has a very complex audio system for its electric light shows. Triggered lightning, playing God with a copper wire. If lightning is so dangerous and unpredictable, how do scientists study it up close without getting killed? The answer lies in one of the most thrillingly dangerous experiments in the history of science: triggered lightning. In places like the International Center for Lightning Research and Testing in Florida, scientists essentially bait the sky. They launch small, black powder rockets trailing a long, thin, grounded copper wire into the heart of a passing thunderstorm. This wire is only a few hundredths of a millimeter thick, thin enough to easily break. But that is the whole point. The rocket ascends, trailing the wire. When it enters the intense electrical field of the storm cloud, the copper wire acts as a perfect conductor. It creates a preferential path for the lightning. In a fraction of a second, the sky fires a massive bolt of lightning directly down the wire to the research tower, hitting the instruments with pinpoint accuracy. This is not just a stunt. Triggering lightning allows scientists to study the return stroke in incredible detail, measuring the current, the voltage, and the electromagnetic fields with equipment placed just meters away from the impact point. It has led to profound discoveries about how lightning attaches to objects on the ground. For instance, they discovered that before lightning even hits a structure, it generates corona discharges, small flickering glows of electricity at the tips of the structure, reaching out to meet the downward leader. Triggered lightning tests are crucial for engineering. The data helps us build better lightning protection systems for our homes, our airports, and our power grids. It is a story of humanity, pitting our intelligence against the most primal force of nature and tricking it into performing for us, if only for a split second. The silent explosion, when trees explode from within. One of the most haunting sights after a thunderstorm is a tree, its bark violently stripped away, shredded into long ribbons, lying scattered across the ground like discarded clothing. It looks like a bomb went off, and in a way, one did. When lightning strikes a tree, it is not just burning it. The lightning is incredibly hot, hotter than the surface of the sun. The sap inside the tree is a liquid, and like all liquids, it contains water. When the lightning bolt enters the tree, it travels down the path of least resistance, which is usually the moisture-laden layer of sapwood just beneath the bark. The incredible heat of the bolt instantly vaporizes the sap and the moisture inside the cells, turning it into superheated steam. Now, here is the physics of destruction. Steam occupies about 1,600 times the volume of the water it was made from. That expansion happens virtually instantaneously. The steam builds up immense pressure inside the trunk of the tree, far beyond what the wood fibers can contain. This causes a violent, explosive steam explosion that literally tears the bark off the tree and can split the entire trunk in half, sending razor-sharp wooden shrapnel flying in all directions. If the tree survives, which is rare, the path of the lightning leaves a deep, spiraling groove in the wood where the bark was blasted away. In a few rare cases, the heat is so intense that it can turn the tree's sap into a black, glass-like substance internally. So, when you see a shredded tree after a storm, remember, it didn't just catch fire. It exploded from the inside out because of the sheer, unbearable heat of a 1,000,000-volt steam engine. The global electric circuit, Earth as a giant battery. We tend to think of thunderclouds as isolated batteries, discharging their energy to the ground. However, there is a bigger picture. Earth itself is a component in a massive, planet-wide electrical circuit, known as the global electric circuit. Here is how it works. Every single thunderstorm on the planet acts as a generator. These storms, roughly 1,000 of them active at any given time, drive a continuous electrical current upward into the ionosphere. They push positive charge up into the upper atmosphere, making the ionosphere positively charged relative to the Earth's surface. Consequently, the Earth's surface carries a net negative charge. We are essentially living on a giant, negatively charged sphere, separated from a positively charged layer of the atmosphere by a massive insulating gap of air. This gap, the fair-weather atmosphere, isn't a perfect insulator. It has a slight electrical conductivity, mostly due to cosmic rays creating ions in the air. Therefore, a constant, incredibly weak electric current flows from the ionosphere down to the Earth's surface, all over the globe, even on clear, sunny days. This current is tiny, about a few picoamperes per square meter, but over the entire surface of the Earth, it represents a continuous flow of nearly 1,500 amperes of electricity. We are bathed in this electric field every second of our lives. On a clear day, the electric field near the ground is roughly 100 volts per meter. You don't feel it because your body is a conductor and you equalize with the environment. But it is there. This circuit is so fundamental to our planet that we are only just beginning to understand how it impacts cloud formation, cosmic ray interactions, and even biological processes. The lightning we see is just the violent, visible spasm of a much larger, silent, and continuous dance of electricity that connects the ground to the edge of space. The metal bird and the bolt, lightning and aviation. Returning to the scenario we started with, the airplane being struck in mid-air. This happens more often than you might think. Every commercial airliner is struck by lightning, on average, once a year. Pilots often see a bright flash, hear a loud bang, and then the event is over. How does a metal tube full of people survive a direct hit from a billion-volt lightning bolt? The secret lies in the Faraday cage principle. The aluminum or composite skin of the airplane acts as an excellent conductor. When lightning strikes the aircraft, the electrical current does not travel through the interior, through the passengers, or through the fragile electronics. Instead, it travels along the outside surface of the metal skin, across the fuselage, and exits out the tail or the wingtip. It essentially bypasses the inside of the plane completely. However, the fuel tanks are a concern. To prevent sparks from igniting the fuel vapors inside the tanks, the outer surfaces of the tanks and the fuel lines are carefully grounded and shielded. Furthermore, the fuel itself contains additives that dissipate static charge. Modern planes are also equipped with static wicks. These are small, trailing metal rods extending from the trailing edges of the wings and tail. They allow the plane to gradually discharge the accumulated static electricity it picks up by flying through the charged atmosphere, minimizing the chance of a catastrophic charge buildup and making the plane more receptive to a single, clean strike. Still, a lightning strike is a serious event. It can leave minor burn marks or small indentations on the metal skin, known as divots. In the rare case of a swept stroke, where the lightning attachment point moves along the plane as it flies, the damage can be more severe. But thanks to rigorous engineering and decades of study, your aircraft is designed to take the hit and keep flying. It is a testament to human ingenuity that we have managed to tame the same force that could easily strike us down. The psychology of the storm, gods, myths, and fear. Finally, we cannot explore lightning without acknowledging its profound impact on the human psyche. Before we understood the physics of charge separation and stepped leaders, lightning was the ultimate symbol of divine wrath. Every ancient culture had a god of thunder and lightning. Thor with his hammer Mjolnir, Zeus with his thunderbolts, Indra with his Vajra, the Yoruba god Shango, who hurled stone axes from the sky. Lightning was the signature of the gods, a tool of punishment and a sign of power. This deep-seated fear has a scientific name: chronophobia, the persistent, irrational fear of thunder and lightning. But is this fear truly irrational? Thunder is loud, startling, and preceded by a flash that can temporarily blind you. Evolutionarily, it makes perfect sense. Our ancestors who feared the storm and sought shelter were more likely to survive and pass on their genes. That primal fear is hardwired into our nervous system. There is a specific physiological response to a close lightning strike. The sudden, massive air pressure change can create a feeling of intense anxiety, a racing heart, and an overwhelming urge to flee. The sound of a lightning strike is not just a sound. It is a physical shockwave that hits your entire body, rattling your chest and bones. It triggers the fight or flight response on a level that few other natural phenomena can match. But there is also a hypnotic beauty to it. We chase tornadoes and storm chasers brave the elements just to capture the perfect lightning photograph. This duality, the terrifying and the mesmerizing, is what makes lightning so compelling. It kills and it creates. It frightens and it fascinates. It reminds us of our smallness in the face of the cosmos, yet inspires us to understand it, to chase it, and to engineer our lives around its unpredictable dance. Conclusion of Part 2. We have journeyed to the outer edges of the solar system, into the hearts of erupting volcanoes, and down to the microscopic steam explosions inside a tree. We have seen lightning as a celestial signal, a volcanic spectre, and a crucial component of the planet's electrical heartbeat. But even after all of this, the questions remain. How much more is there to discover about the lightning on Jupiter? Can we truly predict volcanic eruptions by monitoring its electric whispers? And as our climate changes, will this global electric circuit shift, altering the very frequency and ferocity of the storms that pass over our heads? The mystery of lightning is not a closed book. It is a living, breathing, crackling story that is still being written. Every flash that rips across the sky is a chapter, and every thunderclap is a sentence, challenging us to read further, to understand deeper, and to never lose our sense of awe. This has been AI Besoy, taking you beyond the visible, into the extraordinary. If these facts have sparked your curiosity, if they have made you look at the next storm cloud with a new sense of wonder, then our work here is done. Stay curious, stay fascinated, and never stop questioning the electric universe we live in. Until next time, keep looking up, but remember to take cover if you see the flash. Goodbye, and thank you for listening. Superbolts. When the sky unleashes its nuclear fury. For decades, scientists believed they understood the upper limits of lightning's power. They knew that an average bolt carried about 300 million volts and could light a 100-watt bulb for 3 months. But in the 1970s, satellite data revealed something that shattered these assumptions. A class of lightning so ridiculously powerful that it redefined the word extreme. These are called superbolts. A superbolt is a lightning strike that is at least 100 times more energetic than a typical bolt. But some superbolts go even further, reaching energies up to 1,000 times greater. These are not your average flashes. A superbolt can release energy equivalent to a small nuclear bomb detonating in the atmosphere. They are so bright that they can be easily seen in broad daylight, and they are so powerful that they have been known to melt the metal frames of ships and tear massive craters into the ground. Where do these monsters come from? Superbolts are primarily observed over specific regions: the North Atlantic Ocean, the South Atlantic, and the Mediterranean Sea. Scientists believe they occur during particularly winter thunderstorms, where the charge separation is abnormally high and the cloud tops are extremely cold. But the strangest discovery is that superbolts often originate from clouds that are relatively small and unassuming. They pack the punch of a giant in the body of a dwarf. The physics of how these tiny clouds generate such immense power remains one of the great unsolved mysteries of atmospheric science. A single superbolt carries so much current that it can interfere with the Earth's magnetic field, creating ripples that travel across the entire planet. Lightning and the origin of life, the electric spark of creation. We have spoken about lightning as a destroyer, but what if it was also a creator? What if the very flash that terrifies us was the same flash that brought us into existence? Let us travel back in time, billions of years ago, to the early Earth. The atmosphere of primordial Earth was vastly different. It contained almost no oxygen. It was a toxic brew of methane, ammonia, water vapor, and carbon dioxide. The surface was bombarded by intense ultraviolet radiation from the sun, and the skies raged with constant, violent thunderstorms. The lightning on that ancient Earth was far more frequent and far more intense than it is today. In 1952, two scientists, Stanley Miller and Harold Urey, conducted a famous experiment. They sealed a mixture of these primordial gases into a glass apparatus and sent continuous electric sparks through it, simulating lightning. After just 1 week, they made a stunning discovery. The sparks had transformed the simple gases into complex organic molecules, including amino acids, the fundamental building blocks of proteins, and the very stuff of life itself. This experiment, known as the Miller-Urey experiment, proved that lightning could easily create the chemical precursors necessary for life. It suggests that every time a bolt of lightning flashed across the primordial sky, it was essentially a tiny chemistry factory, churning out the ingredients for DNA and proteins. Over millions of years, these molecules concentrated in the ancient oceans, eventually combining to form the first primitive cells. Could it be that we are all, quite literally, children of lightning? The theory is compelling. Every time you look at a storm, you are witnessing the exact same process that may have birthed your own distant ancestors. The energy that powers your brain, the very structure of your cells, may owe its existence to a spark that ripped across the sky 3 billion years ago. Lightning was the match that lit the fire of evolution. Lightning as the gardener, fire, renewal, and ecological balance. Beyond the origin of life, lightning continues to play a profound and often overlooked role in shaping the ecosystems of our planet. It is not just a destroyer, it is a gardener, a sculptor, and a healer of the land. Consider the phenomenon of forest fires caused by lightning. In the public mind, wildfires are disasters, but ecologically, they are a vital and necessary part of many forest ecosystems. Certain species of trees, such as the giant sequoia, have cones that are sealed with a thick resin. These cones will only open and release their seeds when exposed to the intense heat of a lightning-caused fire. Without lightning, these majestic trees would eventually go extinct. The fire clears away dead underbrush, enriches the soil with ash, a natural fertilizer, and opens up the forest canopy, allowing sunlight to reach the forest floor and nourish new life. Furthermore, the nitrogen fixation we discussed in Part 1 is massively amplified during intense lightning seasons. A single year of heavy lightning activity can pump millions of tons of bioavailable nitrogen into the soil, creating a natural fertilization event that boosts plant growth across entire continents. Lightning also serves as a natural immune system for the Earth. By igniting fires, it prevents the unchecked accumulation of dry biomass. Without lightning fires, forests would become so dense and choked with dead wood that when a fire eventually did start, perhaps from human activity, it would be a cataclysm of unprecedented scale. Lightning, in its brutal and chaotic way, maintains the long-term health and resilience of our planetary ecosystem. It strikes, it burns, and in the ashes, it plants the seeds of tomorrow. The Global Lightning Detection Network, an invisible web. How do we know where and when lightning strikes? In the old days, we relied on weather stations and visual observations. But today, we have an invisible, planet-spanning web of sensors that catch every single flash, no matter how remote. The Worldwide Lightning Location Network, or WWLLN, is a consortium of over 70 universities and research institutions. They operate a network of extremely sensitive radio antennas placed in secret, far-flung locations across all 7 continents. When lightning strikes, it emits a powerful, low-frequency radio pulse called a spheric. This pulse travels through the Earth's atmosphere and can bounce between the ground and the ionosphere, effectively traveling halfway around the world. By measuring the exact time it takes for these spherics to reach 3 or more of these listening stations, computers can triangulate the precise location of a lightning strike to within a few hundred meters, anywhere on the planet. The system operates 24 hours a day, 7 days a week, processing hundreds of thousands of lightning strikes daily. Above the WWLLN, we have the satellites. The Geostationary Lightning Mapper, GLM, aboard the US GOES weather satellites, stares down at the Americas from 35,000 kilometers in space. It takes over 500 images per second, looking for the brief, bright flashes that signal a lightning strike. It doesn't just detect strikes, it maps the entire evolution of a thunderstorm in real time, watching how lightning activity surges and wanes as a storm intensifies. This data is not just for scientific curiosity, it is a lifesaver. By monitoring lightning frequencies, meteorologists can predict the sudden intensification of tornado-producing storms up to 10 minutes before they happen. Those 10 minutes can mean the difference between life and death for communities in the path of destruction. We are no longer blind to the sky. We are watching its every heartbeat. Human-made lightning, the unintentional experiment. Here is a deeply unsettling thought. We are not just observers of lightning, we are also creating it. As our cities expand and our industries grow, we are fundamentally altering the electrical dynamics of the atmosphere, often with consequences we do not fully understand. Consider the phenomenon of urban lightning. Research has shown that large metropolitan areas, with their vast expanses of concrete and steel, generate urban heat islands. These areas are significantly warmer than the surrounding countryside. This extra heat fuels stronger updrafts, which in turn create more vigorous thunderclouds. Studies in cities like Houston, Texas, and Kuala Lumpur have shown a measurable increase in lightning frequency directly downwind of the city center. We are literally heating the sky and making it angrier. Even more directly, wind turbines are becoming accidental lightning rods. A wind turbine is a massive, rotating structure of conductive materials, often built on exposed ridgelines or offshore in the middle of the sea. They are the tallest objects in their vicinity, making them irresistible targets for lightning. It is estimated that every wind turbine is struck by lightning between 1 and 10 times a year. Engineers have had to design sophisticated systems to channel this massive energy away from the sensitive generators and safely into the ground. But the sheer frequency of these strikes provides a rich data source for scientists studying how lightning interacts with our infrastructure. And then there are the power lines. The massive transmission lines that crisscross our countries act as giant antennas. They attract lightning and, just as importantly, they generate their own corona discharges during storms. These human-made structures are continuously shaping and distorting the electrical environment of the planet. We are, in a very real sense, writing our own electrical signature into the sky. The silent electromagnetic pulse, the grid's greatest enemy. When lightning strikes near a power line, it does not just cause a brief flicker of your lights, it can destroy the entire grid. This is because lightning is a massive electromagnetic pulse, EMP, and our modern world is utterly dependent on fragile, sensitive electronics. Let us explain how this happens. When a lightning bolt travels through the air, it is not just a flow of electrons, it is a moving wave of electromagnetic radiation. This radiation travels outward from the strike, like ripples in a pond. These ripples, called electromagnetic transients, are picked up by any conductive wire in the vicinity. The wires act as massive antennas, absorbing this electromagnetic energy and converting it into a sudden, massive surge of electrical current. This surge, known as a voltage spike, travels down the wire and enters every piece of equipment connected to it: transformer stations, computers, hospital equipment, and even the delicate circuits inside your home. A direct lightning strike on a substation can cause millions of dollars in damage and plunge a city into darkness for days. But it is the indirect strikes that are often the most insidious. A strike a kilometer away can still induce a powerful enough surge to fry the circuit boards of an entire office building. To combat this, the power grid is fortified with surge arresters and lightning protection systems. But as our grid becomes smarter and more digitized, with millions of tiny, interconnected sensors and microprocessors, it becomes exponentially more vulnerable. A single, well-placed lightning strike could theoretically cascade across a network, triggering a continent-wide blackout. It is a modern vulnerability that few people ever think about, yet it is a sword of Damocles hanging over our hyper-connected civilization. The future of lightning science, lasers, rockets, and quantum leaps. If we can't stop lightning, can we control it? For decades, the idea of manipulating the weather has been the stuff of science fiction. But today, scientists are actively experimenting with ways to steer and even trigger lightning at will, moving beyond simple copper rockets. The most revolutionary technology on the horizon is the laser lightning rod. Imagine firing a high-powered, pulsed laser beam into a thundercloud. The laser creates a thin, conductive plasma channel in the air, a virtual, invisible wire that reaches all the way to the sky. This plasma channel is an ideal path for electricity. If a thundercloud is about to discharge, it would preferentially choose this easy path over the unpredictable, jagged path it normally takes. Early experiments in the Alps and in New Mexico have shown promising results. Such a laser could be installed on top of an airport, a rocket launch pad, or a nuclear power plant to actively and safely discharge the storm before it can cause damage. It would be like putting a giant, invisible umbrella of protection over critical infrastructure. Beyond controlling lightning, scientists are also investigating ways to use lightning for quantum communication. The electromagnetic waves emitted by lightning travel great distances and carry information about their source. By analyzing the subtle distortions in these signals, researchers are developing new ways to study the ionosphere and the Van Allen radiation belts. And then there is the Holy Grail, harvesting lightning energy. For generations, dreamers have asked the question, if a single bolt has 1 billion volts, why can't we just capture it? The answer is physics. A lightning bolt, while incredibly powerful, is unbelievably brief. It lasts microseconds. To capture its energy, you would need a supercapacitor capable of absorbing an astronomical spike of power in an impossibly short time. Currently, such technology does not exist. The energy in a single bolt, if averaged over a whole day, is roughly equivalent to the cost of the gasoline needed to drive a car a few miles. It is not worth the effort, and the technology is centuries away from being viable. But the pursuit of this dream drives innovation in power electronics, materials science, and energy storage. Even if we never capture a single bolt, the journey of trying will give us batteries that charge in seconds and materials that can withstand the heat of a star. The lightning that never ends, the Jovian secret. We have reached the edge of our knowledge, but the universe has one final surprise for us. We know that lightning exists on Jupiter, but recent data from the James Webb Space Telescope has hinted at something even more astonishing: persistent lightning. On Earth, lightning is an event. It strikes, it flashes, and it is gone in an instant. But in the deep, thick atmospheres of gas giants, scientists are finding evidence of storms that sustain continuous, relentless electrical discharge. Imagine a storm that never stops, where the lightning flashes in a constant, unending strobe, powering the circulation of the entire planet's atmosphere. This persistent lightning is thought to exist deep beneath Jupiter's outer clouds, where the atmospheric pressure is thousands of times greater than Earth's. The ammonia and water clouds are so dense that they trap heat, creating perpetual convection currents. The lightning that results is not just a random bolt, it is a fundamental part of the planet's heat engine. Understanding this constant, infinite lightning could help us understand the very structure of these alien worlds. And if there is persistent lightning on Jupiter and Saturn, could there be similar phenomena on the billions of exoplanets now being discovered in our galaxy? Some scientists theorize that super-Earths, or mini-Neptunes, may have atmospheres so charged and so energetic that their skies are permanently ablaze with electrical fire. We cannot see them yet, but the radio telescopes are listening. One day, we might detect the radio crackle of lightning from a world hundreds of light years away, confirming that our electric phenomenon is not unique to our pale blue dot, but a universal constant of the cosmos. The human condition, finding peace in the storm. We have dissected the physics, mapped the frequencies, and stared into the heart of the electrical storm. We have seen lightning as a god, a monster, a creator, a gardener, and an enemy of our digital world. But what does it all mean for us, the fragile humans who watch it from the ground? There is a reason we still gather on our porches to watch a lightning storm. It is a moment of pure, undistracted connection to the raw power of existence. It reminds us that the world is not just a set of equations on a blackboard. It is a living, breathing, violently beautiful system. When you stand at the edge of a storm, you are witnessing the planet flexing its muscles. You are watching the release of pent-up energy that has been building for hours, a cosmic sigh of relief from the sky. It is a reminder that nature does not care about our plans, our schedules, or our worries. It does its thing, indifferent to our presence, and yet, it is the very reason we are here. The fear of lightning, the keranophobia we spoke of, is not a flaw. It is a gift. It is the echo of our ancestors, a primal alarm that kept us alive. But the wonder of lightning is what makes us human. It is the spark that drives us to ask, why? It is the curiosity that makes us launch rockets into storms and lasers at the clouds. Conclusion of the Odyssey. We have now completed our great electric odyssey. We have traced lightning from the microscopic collision of ice crystals to the vast, swirling storms of Jupiter. We have seen it create life, shape continents, and threaten our most advanced technology. We have stood in awe of its power and scratched our heads at its mysteries. What have we learned? That lightning is not just an event, it is an eternal presence. It is the blood of the sky, the crackle of creation, and the roar of the infinite. It strikes in an instant, but its impact lasts for eons. The next time you see a flash on the horizon, pause for a moment. Do not just cover your ears. Listen. Look. Feel the thunder roll through your bones. Know that you are standing on the surface of a giant, electrically charged sphere, hurtling through space, protected by a fragile layer of air. And for a brief, terrifying, and beautiful moment, that fragile air is set ablaze by the greatest show on Earth. This has been Night Tales Docs, concluding our three-part journey into the mesmerizing world of lightning. We hope your curiosity has been sparked, your perspective shifted, and your appreciation for the sky above you forever deepened. Thank you for listening. Stay curious, stay safe, and remember, the universe is electric. Until we meet again, keep looking up.